Every woodworking project is actually an engineering project. Whether you're building a dining table or a cutting board, you're dealing with forces, friction, tolerances, physics, all kinds of engineering principles. The funny thing is, most of us don't ever think of it that way. We blame ourselves when something doesn't fit, or we blame our tools. And if the tabletop cracks, it was the wood. But usually there's an engineering principle behind what happened. Tonight, I'm sharing 15 engineering concepts that have completely changed the way I build. And once you understand them, you'll start seeing them everywhere. The first concept I want to talk about is mechanical advantage. Now, these are big words for a simple concept. What this means is using a tool or a mechanical device to increase the force of whatever you're doing. So for example, if I'm trying to take two boards and push them together to put glue between them, I can only push together with so much force with my hands holding those boards together. But if I get a clamp that has a twisting screw in it, that allows me to apply a fine twisting force, which will push those clamps together and give me thousands of pounds of pressure. This is the same concept of how a vise works. When I push down on the arm of that vise, I am multiplying the clamping force that goes into whatever I'm holding. Another great example of this is a breaker bar or an extension on your torque wrench. If I need to unscrew something that's really snug on there, I can use a screwdriver and try to twist it with my hands, or I get a big arm on a torque wrench, and the longer that arm is, the easier it is to move. Another really simple application of this concept is a wedge. When you tap in a wedge with a hammer, you're taking a force and applying it this way, but that force multiplies and increases significantly, pushing outward. That's why you can tap in a wedge and it'll serve as a great clamp. This is how an axe or a hatchet head works, is it forms a wedge, and as you push down on it, it pushes the two pieces of wood apart, which is why you can split really big logs with a small wedge. Now, a sub-concept of mechanical advantage is leverage. Leverage is the critical component for a hammer or a pry bar. One of the most obvious examples of leverage in woodworking is using a hammer to pound in a nail or to pull out a nail. If you pound in a nail like this, holding the handle at the very end, where you're just hitting it like that, you can't hit the nail in very hard. But if you slide your hand back and you swing it, that leverage of that longer length of the arm is what's going to give you that extra power and velocity. The same thing is true for pulling out nails. If you take a hammer and you hold it at the base and try to pull out a nail like that, you're not going to be able to do that unless it's a pretty weak nail. But if you hold it at the end, you have all this length here. All that leverage will help you to pull that nail out much easier. And if you can't get it with a hammer like this, you can always use a pry bar like this. This will make it so you can apply a little bit of force at this end, and there's a ton of force down at this end. This has a long lever arm, and the reason the bottom is shaped like this is so that you have a fulcrum built into it. You just put this right on the ground and pry it back, and you have a lever, you have a fulcrum, and you have the lifting point. That's going to give you maximum leverage to move or lift whatever you need to lift. Triangles are awesome. Anytime you're building something that seems a little bit wobbly, it probably needs a triangle. Triangles are used in all types of engineering applications. If you look at skyscrapers, bridges, big buildings, and even something as simple as the gate on your fence, you'll find that triangles are key. If you want something to not sag, rock, wobble, or any of that, add a triangle brace and it will make it solid. Triangles are also the reason why a three-legged stool never wobbles. If you're building something with two sides or two legs, a top and a bottom, without any kind of bracing, eventually it'll start shifting and moving. The best way to counteract that is to put in a triangle. If you don't want to have triangles in your design though, and you still want it to be strong, the other thing you can use is a shear wall. Now this is something used commonly in construction as a way to prevent racking on a wall. And they basically take a piece of plywood or OSB and they nail it on to the side of the framing. And that shear wall does the same thing as a triangle. In order for it to work though, you have to glue, nail, or screw those edges all the way around so there's no movement. You see this most commonly on the backs of cabinets or bookcases. Next up is load paths. Now, weight on an object or a piece of furniture usually goes down because of gravity, but it follows what's called the load path. This is the path that the weight travels through the piece of furniture. So if I have a table with a leg on each of the four corners and I put a weight in the middle, that weight will actually travel through the tabletop into the legs down into the floor. If anywhere in that load path you have a weak link or a weak joint, that will be the most likely point of failure. So any weak points in that load path should be strengthened. Related to load paths is load distribution. If you want to prevent damage to a certain area because of leverage or clamping, load distribution is the concept of spreading out that load from one single point to a much larger area. This is why I use clamp blocks blocks when I'm trying to set up a glue up. Then you spread out the force instead of having it concentrated in one area where it can cause damage. If you're ever trying to pull a nail out of something where you don't want to scratch the surface, use another block of wood under the hammer where you're prying it back and you won't mar the surface at all. Next up is center of gravity. Now everything that has weight has a center of gravity. So for example, with this ruler here, if I want to find the center of gravity, I just put my fingers at either end and I slowly slide them in, and it will naturally end up at the center of this ruler, which happens to be 6 inches on a 12-inch ruler. If the center of gravity is low in an object, it's less likely to tip over. If I'm building a bookcase and I put a cabinet at the top of the bookcase where there's a lot of weight, it's going to be more likely to tip over. But if I put the cabinet at the bottom, that gives it a solid foundation and it's a lot harder to push it over. The point at which an object tips is when the center of gravity is past the pivot point. So as I lean it over, that center of gravity goes past the pivot point at the bottom, it tips. If you put heavier items lower, it's much harder to tip. Now let's talk about friction. Friction is good sometimes and bad sometimes. Friction keeps clamps and bench dogs from moving, it holds your work in place, and it keeps tools from flying out of your hand. But sometimes you want to minimize friction. Anytime your blades or cutting tools get really hot, that increases the friction. If you have wood resin or buildup on your blades, that's causing friction, which will burn your wood. You don't want any friction on the top of your table saw or your bandsaw, but you do want friction on your push sticks. Know where you want friction and where you don't. Tolerance stack up. This is an important one. When you cut something, there's always a certain amount of tolerance. If I try to cut a board at exactly 1 inch, I can only get so close. It's usually just slightly more or slightly less than that. That difference from 1 inch to the actual cut that I make is called the tolerance. When you do that over 10 boards and that tolerance gets added together, that's called tolerance stack up. And that is the primary reason why projects don't fit together. Usually you have some kind of tolerance stack up in your assembly, and once that gets all added together, it just won't fit. One of the easiest ways to avoid tolerance stack up is to start from one face of the project and measure everything from there. This is called your reference face. When you do that, you prevent that minor error from stacking up across multiple measurements. Instead of measuring from both edges of something, mark one side as your reference face and measure everything from there. A good set of engineering drawings will always call out a reference face in each of your 3 dimensions. Now, wood movement is a critical one that I've actually done an entire video on in regards to pocket screws. But in a nutshell, when you have a board, it's going to expand across the grain like this. It does not expand in length. So you have to account for that expansion across the grain. Imagine a piece of wood like a handful of straws. And as the water goes in and out of those straws, it's going to expand the straws. They're going to grow and shrink depending on where the moisture is. That can happen over time. That can happen in your house. That can happen if you move from a humid climate to a dry climate or vice versa. There's a lot of things that can cause that movement. So when you do woodworking or design a piece of furniture, you have to account for that. So if you have something that expands this way and you take that and you glue another piece on top of it that expands the other way and does not expand this way, then you may start seeing cracks or see things start to separate. As long as you account for that when you're building, you should be good. Stress concentrations. Cracks usually start at a corner. This is because when a joint is loaded or there's weight put on it, tons of force is concentrated into that sharp corner. That causes premature failure, and that's actually the reason why airplane windows are rounded. When you round the corner, you spread out that stress concentration over a larger area. You can also drill relief holes at the end of cuts. Next up is beam deflection. Why does the board sag one way but not the other way? It's mainly because the deflection or the sag on the board is largely determined by the thickness in that dimension. So the sag on a board like this that's 3/4 of an inch thick is going to be much more in this direction than it will be in this direction because now it's 3.5 inches thick. To figure out what this deflection is, you can either guess by pushing on it, you can over design the heck out of it and just make it really beefy and strong, or you use my favorite little tool called the sagulator. This is a website where you can plug in materials, thicknesses, dimensions, and anything else related to a shelf. And it'll tell you based on the weight that you put on it, how much it's going to deflect or sag. Another really important one is designing for assembly. Good projects don't just look good in their final state, but they go together easily. Dados, rabbets, alignment pins, all of that reduces frustration during glue up. Before cutting anything, ask yourself, how am I going to assemble this? What I like to do is walk through in my mind the step-by-step process of how I'm going to put it together. The worst example of this I can give from my own experience is a big bookcase I was building where I tried to put it together and I thought I had figured out how I was going to put the shelves in, but it turns out the corners of the bookcase were too close together for me to fit these shelves in after the fact. I should have designed it to be able to slide slide in much easier. In order to fix it, I had to do a lot of trimming, sanding, and I did have to get a bigger hammer. Another thing you can do that will really help is remove variables. Anytime you can use a stop block for cutting something so that you're not measuring every time, or a jig to make repeated cuts. All of those are removing variables in your build process, which will make you much more consistent. Use templates, use jigs, and measure less. Now, the very last engineering principle that I want to tell you about that's kind of a bonus tip is engineers know really well how to minimize their mistakes. And I know this from experience. Engineers don't like to be wrong, and they don't like people to highlight their mistakes. So we get really good at minimizing them or making them seem less important. You can also minimize your mistakes by preparing and thinking through the process. If you plan out your assembly, if you label your parts, if you create jigs, if you dry fit before glue up, all those things will help to minimize your mistakes so you don't have to deal with that later. If you do make a mistake, the good engineers know how to make that mistake seem less of an issue. Just figure out how to hide it, how to turn it around, put it on the back of the piece, or something to make it not as visible. And usually, unless it's really obvious, most people won't even know. The more I build, the less I think that woodworking is about making perfect cuts. It's really about understanding why and how things work. Once you start understanding and really recognizing these engineering principles, you'll make better decisions before you even turn on a tool. And in my experience, that's what really differentiates somebody that can just build from plans to someone who can design and build their own projects. That's where it gets fun. If you've never tried to design and build your own project, don't worry. It's not as hard or scary as you think. I'd recommend starting with something small to begin with, but then you can build from there. Now, I would love to hear from you to hear which of these principles has saved you the most frustration in your shop. Or is there another critical engineering concept that I didn't cover? I know we have a lot of engineers out there, so let me know if I forgot something. Now, go build something, and we'll see you next time.